Welcome. Let's take a look at an example here. It's a bit long to read, but we're going to go ahead and read through it. So an airline is trying two new boarding procedures, option 1 and option 2, to load passengers onto their Long Beach to San Francisco flights. Since option 1 has less automation, the airline suspects that the mean option 1 loading time is greater than the mean option 2 loading time. To investigate, the airline selects a random sample of 205 flights from Long Beach to San Francisco using option 1. And I'm going to start highlighting some things here. So there's our 205 flights that they sampled. The sample mean was 18.5 minutes for that loading time. And we're assuming that the population standard deviation is 4.3 minutes. And then they also select an independent random sample of 295 flights from Long Beach to San Francisco, now using option 2 to load passengers, record the loading times, and the sample mean is found to be 17.5 minutes, and we'll assume the population standard deviation is 5.7 minutes. All right, so at a 1% level of significance, is there sufficient evidence to support the claim that the mean option 1 loading time is greater than the mean option 2 loading time for this airline's flights from Long Beach to San Francisco? All right, we'll let our first population be times using option 1. So let's go ahead and write our claim here first. So the claim they're testing is that the population mean loading time for option 1 is greater than the population mean loading time using option 2. So our null hypothesis will be that they are actually equal. So we're going to, as always, assume the null hypothesis is true at the start, and then see if the collected data convinces us otherwise. All right, so let's summarize the given values here that we highlighted. So sample size using option 1. So we just do subscripts here, N1, 205. That's sample mean, X bar for population 1. So the sample mean, sample taken for the option 1 loading times, that came out to be 18.5 minutes. And we're assuming the population standard deviation, sigma 1, is 4.3. And then option 2, so subscript 2 there, 295 flights. For that sample data, the mean was 17.5 minutes, and we're to assume that population standard deviation is 5.7 minutes for option 2. All right, so we're conducting a hypothesis test of two population means where samples were taken independently. So it's going to be a 2 sample. And our choice will either be Z or T, as we did previously when we were looking at just one population. So we're going to see if the standard deviations of the populations were provided, and they were. So it's going to be a 2 sample Z test. If we did not know our population standard deviations, then instead of Z, we would go with our T distribution. So just like what we had done previously. So in this case, we're doing 2 sample Z test because sigma 1 and sigma 2 are known. So the test is actually going to look at the difference in the sample means, and then we'll convert that to the test value using our calculator. But let's go ahead and look at the difference in the sample means. So option 1, the mean loading time was 18.5 minutes, minus option 2 was 17.5 minutes. So there is a difference here, and I'm writing units just to make sure we know what we're talking about. So there's a difference of 1 minute in terms of loading times. So the sample mean was 1 minute higher than for option 1 than it was for option 2. So we want to see if that evidence is enough to convince us that this claim is true. So we'll find the test value by going to our calculators. So let me get my calculator up here. So stat tests, going to our 2-sample z-test. You want your input to be stats. We don't have the actual data for these 205 and 295 flights. That would be a lot of data. So stats. And then sigma 1, you want to enter 4.3, sigma 2, 5.7, and sample mean 18.5. And then N1 was 205. And then sample mean for option 2. And sample size 295 for option 2. And then we have our right tail test, mu1. Make sure you have greater there. And then, as always, we can do calculate or draw. I'm just going to go calculate here. And the z-score we see there is our test value. So I said round to 3 places here. Often we do 2. So we can just do whatever directions are provided. So 3 places would be 2.234. And then the p-value with that test, we'll do 4 places as we usually do, 0.0127. And that as a percent would be 1.27%. All right, so we compare our p-value to our significance level alpha. So we're comparing that to 1%, that's our alpha. So in this case, our p-value is greater than alpha. It might be looking like it's getting close there, but it's still bigger. So when our p-value is greater than alpha, we do not reject the null hypothesis. All right, so at a 1% significance level, we conclude that there is not enough evidence to support the claim that the option 1 mean loading time is greater than the option 2 mean loading time. All right, so let's go forward and see what happens then in the case where we are not provided with the population standard deviations. And the only difference here is that we can no longer use our Z distribution, but calculations would be based on the T distribution. So we are going to use our calculators. I did though write the by hand formula here, and you're seeing S sample standard deviation in the formula. And the T distribution always has an associated degrees of freedom. So because we're going to use our technology on our calculator, we won't have to worry about calculating the degrees of freedom, but I did just put for reference here how to find it. And then our usual requirements that our populations are normal or our sample sizes are reasonably large. Now, the only other thing that we need here for our 2-sample T test that we haven't seen previously is we need to assume, well, we will assume that the variances of our populations are not equal. So when we assume that the variances are not equal, we say that we're not going to pool them. So on our calculator, it's going to ask you if you'd like to pool, and the answer is no. So pooling would mean that we're assuming the variances are the same. So that's all you need to know about that part. We just need to know what to enter when we get to it. So let's take a look at the example here, number 1. All right, the mean age of a random sample of 22 people playing slot machines. Let me go back to highlighting here. 22 people playing slot machines. The mean age was 48.5 years with a standard deviation of 6.8 years. So for these 22 people, this was the mean age with this standard deviation. So that standard deviation, it says specifically, is for that sample of 22 people. And then we went on to take a look at 33 people playing roulette. The mean age there was 53.5 years with a standard deviation of 3.2 years. And based on this data, can we conclude at a 1% level, significance level, that the mean age of slot machine players is less than the mean age of roulette players? All right, and we'll let our first population be our slot machine players. All right, so let's write our claim here. So the claim that they're testing is that the mean age of all slot machine players is less than, so less than the mean age of all roulette players. So the null hypothesis will be that they are equal. And then we'll summarize the given information. So for the slot machine players, our first population, we had N, so N122, X bar 48.5, subscript there, 1. And then that standard deviation again was for that sample of 22. So that's our sample standard deviation. And then for roulette, we had 33 people in the sample. The mean came out to be 53.5 years. And the standard deviation for those 33 people, so the sample standard deviation was 3.2 years. All right, so in this case, we're running a 2-sample, so it's a t-test because sigma 1 and sigma 2 population standard deviations are unknown. So the most important thing here is when you're reading that question to ask yourselves, is that the standard deviation for all players, all slot machine players, or was it for that sample? So for these 22, the mean was this with that standard deviation. So it doesn't say assume like it did in that last question that we could assume something. It's just giving us the actual value of standard deviation for the sample. Okay, so the test is still based on looking at the difference of the sample means. So let's see what happens here. So 48.5, the mean age of slot machine players. If I subtract the mean age for the sample of roulette players, see what that is. So 48.5 minus 53.5. So it's coming out negative here. I'm going to write units, negative 5 years, because this mean for slot machine players is 5 years lower than the sample mean for the roulette players. So that's how we're getting a negative value. First number is smaller than the second. And that is an important concept coming up later. But otherwise, we can jump to our calculator and get the test value that corresponds to that. So we just want to make sure to pick our 2-sample t-test. And now when we enter the statistics, a different order than the last screen. So now we're going to enter the sample mean first here for population 1, so 48.5, and then sample standard deviation 6.8, sample size 22. Second population 53.5 for the sample mean, 3.2 sample standard deviation, and that sample size was 33. And this one is a left tail test. So we have our mu1 less than our mu2. And here's the pooled part. So you just want to make sure that says no, and we never change that. So once you have that on no, you're good. And then I'll go ahead and do calculate. All right, so now we're seeing this test value or test statistic is T instead of Z. So we'll do 3 places again. So that would be negative 3.219. And the associated p-value there is pretty darn small, 0.0017. So that is not even 1%. It's only 0.17%. So very small p-value. So that p-value is definitely less than alpha. So alpha was 1%. So comparing it to an alpha of 1%, so that is less. So anytime our p-value is less than or equal to alpha, we are rejecting that null hypothesis. So I'm rejecting the null in favor of the alternative. So based on a sample of 22 people playing slot machines and 33 people playing roulette, and using a 1% significance level, there is enough evidence to support the claim that the mean age of slot machine players is less than the mean age of roulette players. All right, so that ends an example of a 2-sample Z and a 2-sample t-test.